Chapter 11 deals with the whole area of solutions and solution chemistry. What a solution is a mixture of solute and solvent. They are mixtures that have different compositions. Now we tend to only think in terms of a solid dissolving in a liquid, but you can get all sorts of different classes of solutions. So air is a gaseous solution. Vodka is a solution of a liquid in a liquid. Brass is a solid solution. So don't just think of solutions in terms of something like salt and water. Now the major part of this chapter and the main thing that gets asked about is to do with concentrations. And of those, molarity is the biggest one. And we've done lots of work on this. You've done lots of calculations with this. We've also done some work on mass percent and mole fraction. These are two things that have come up. Molality tends to not come up very often. This is the idea that when you're dealing with non-aqueous solutions, you have to consider the mass of the solvent, not the volume of the solvent. In the case of water, molality and molarity are the same because of 1 gram of water weighs 1 kilogram. Normality is not a measure that is really used in APs. So, but the idea of normality is that, for example, HCl, a 1 normal solution equals a 1 molar solution, but in the case of H2SO4, a 1 molar solution actually releases 2 hydrogen ions, so it's a 2 normal solution. Right. The idea is that the energy released when solutions form, or the energy absorbed. Now we did this when we dealt with delta H. Cardinal rule of solubility is like dissolves like. So you've got the concepts of separating a solute into individual components, overcoming the intermolecular forces of the solvent, and then allowing the solute and solvent to interact. So this is the process known as dissolving or solution. So let's just look at that diagrammatically. If you look at, for example, a solute here at the top, it has to become expanded. This is breaking bonds, and so therefore it is both the solute and the solvent are having to break bonds in order to make space for each other. So that is a endothermic process. It requires energy. Bond breaking always requires energy. But then you take those two and you mix them together. Well, that process is bond formation. So the formation of a new solution. So here you've got that diagrammatically, the idea of breaking the bonds initially and then getting that energy back as a result of the new bonds forming. So if the overall energy of dissolving is exothermic, then those new bonds forming, delta H3, is going to be greater than the bond breaking. If the overall process is endothermic, then obviously the energy back is less than the energy required to break bonds. This is why things dissolve generally, because like an aqueous solution is in a much lower energy state than its individual components. Here you've got an example of oil on water, which doesn't dissolve because the energy required to break the bonds between the water molecules is too great to overcome the forces. So what happens is the hydrogen bonding of the water molecules repels the oil molecules, so the oil floats on top. Now, factors that affect solubility are the structures. So, for example, a fat-soluble vitamin A and water-soluble vitamin C. This is an important idea, because if you can end up taking too much vitamin A, and it can store in your fat molecules of your body and store up there. We also tend to think of solubility primarily in terms of a solid dissolving in a liquid, but what about when we dissolve a gas in a liquid? This is an example with Coke. In the case of Coke, what happens, or any sort of carbonated drink, is as the temperature rises, the solubility actually decreases. This is why when you have a carbonated drink in the refrigerator, you take the lid off, a little bit of carbonation comes out, but then as the drink gradually warms up, it carbonates more and more, or the fizz increases. This is why you wouldn't have a warm bottle of Coke and open it, because it's liable to largely empty all at once. This is tied up with something called Henry's law. The piston is pushed down, increasing the pressure, which increases the rate at which the gas molecules enter the solution. This increases the concentration so that a new equilibrium is established. So the higher the pressure, the more gas it will dissolve, which is why carbonated drinks are stored in sealed bottles. And the temperature on solution, everyday experience of dissolving substances like sugar in hot water lead to the misconception that solubility increases with temperature. The rate, and this is where we tie into solubility with rates. Rates will always increase with rising temperature. But solubility, in the case of sugar, does increase with rising temperature, but you can see that some chemicals like Na sodium sulfate will decrease, and we can see definitely with gases that solubility of all gases decreases with rising temperature. Now, solutions have different properties to the pure solvent that they dissolved in. So as soon as you dissolve something in a solvent, its properties change. The effect of non-volatile solutes on the physical properties of solvents can be explained in terms of lowering the vapor pressure of the pure solvent. So what is happening is that the non-volatile solute is interfering with the solvent's ability to evaporate. So if you have water, pure water, what will happen is that it will just evaporate and then condense. But in the case of a solution, an aqueous solution, what will happen is that the water molecules can evaporate and will condense in another container. This is known as Raoult's law. He showed the relationship between vapor pressure of solutions, and he found that a relationship that was observed connected to the mole fraction. Now this has been a big area in AP in the past, but it really hasn't shown up very much at all in recent years. The idea is that if you have a pure solvent, then it will have one vapor pressure. If you have the pure solute, you have another vapor pressure, and there's a direct line relationship between these depending upon how much solute is in the solvent. And this is the relationship between them. It's very just that the mole fraction determines the total vapor pressure. So, but you can get deviations from this. I really don't think this is a big area, but for those who want to study it, I would suggest you have a look in the textbook about the details of this, but it is not something that comes up very often in APs. So you get these deviations from the ideal. We did do a lab earlier in the year on colligative properties, and this has come up in the past. So this is the depression of freezing point and the elevation of boiling point. Colligative properties depend upon the number of solute particles, not their identity. So what they affect, if we look at a phase diagram, is because the vapor pressure has been lowered because of these particles that are stopping the solute evaporating, then what will happen is that the blue line represented here changes. So the overall effect is elevation of boiling point and depression of freezing point. That is a concept you need to understand, and this slide is one worth dwelling upon and thinking about so that you understand the concept. Okay, molarity can be directly calculated, and we actually did a lab involving this, if you remember earlier in the year. Same with freezing point depression. You can directly calculate molality. Questions have come up in the past in APs. Boiling point and freezing point constant, the major one that we tend to use is the water one. But in the lab that you did earlier in the year, we gave you the constants. And if you were asked about KB or KF, you would be given these numbers. A practical application of this is in places like Canada. They spread salt on the road because salt water has a much lower freezing point than ordinary water, so it causes the ice to melt. Same with putting antifreeze into a car radiator. Osmotic pressure is used in biology, so it's the same concept that when you get osmosis, because you've got a pure liquid which will then go across the semipermeable membrane into a solution inside the cell. And so here you've got an example of that from a chemistry point of view. So the height that it raises is the osmotic pressure. The Van Hoff factor is just tied up with this idea that it depends upon the number of particles, not the nature of the particles. So what this means is that a solution involving sodium chloride increases by 2, not by 1, because it breaks up into sodium and chloride ions. So for sodium chloride, the expected Van Hoff factor is 2, magnesium chloride 3, etc. Okay, so this comes into the idea of boiling point elevation, and we did some calculations involved in this when we did the lab earlier in the year. It would be worthwhile pulling that lab out and re-examining it. Colloids, this is the last slide in this, and a colloid is not a true solution. An example of a colloid is a fog. On a foggy night, you can see the light beams passing through the fog because they're diffracted by the particles that are in it. So a colloid is not a true solution. If you shine a light through a true solution, you can't see the beam. Thank you for listening, and I hope that you have a pleasant day.